Okay, good afternoon. No? I think we can start. May tanong ako, ano? Yung mga nasa likod, talaga bang gusto niyo dyan sa likod? Don't you want to come any closer? You prefer being in the back? Okay. Choice ninyo, no? Okay, so we'll continue with our discussion on small signal analysis of transistor amplifiers. And this is what I plan to take up for today. Take up the common emitter and common source amplifiers. So these are very basic amplifiers. And then we'll discuss, if we have time, I think we should have time, common emitter, common source amplifiers with degeneration resistors. Okay, okay, just want to correct something that I mentioned last time. Medyo nagkamali ako last time when I was describing zero input conditions. Nabaliktad ko, no? Nabaliktad ko yung dalawa. It was pointed out by one of your classmates, so thank you for that, no? Yung zero input condition, the idea there is you're suppressing the input. No? In other words, you're reducing the input to zero. So if your input is a voltage source, how do you reduce a voltage source to zero? If I have a voltage source, how do I reduce that to zero? Yeah, you replace it with a short circuit. No? And then if your input is a current source, how do you reduce that to zero? You replace it with an open circuit. No? So medyo nabaliktad ko yung dalawa. So when you have a voltage source, no, you replace it with a short circuit, and when you have a current source, you replace it with an open circuit. So I'm sorry for that. No? Okay, so I hope that's clear. Okay, then we went into a discussion of determining the hybrid pi parameters. So the idea there is you have a linear circuit. This is a two-port network. How do you determine the hybrid pi parameters of this particular linear circuit if you want to represent your linear circuit, no, by the unilateral hybrid pi model? So the first parameter is transconductance. How do we define transconductance? That is output current divided by input voltage at full load condition. If we are determining transconductance, what is our no load condition? Okay, ano yung definition of no load? We said no load is there is zero power being delivered at the output. So if we are determining transconductance, what should be our no load condition? Anyone? Should it be open or should be shorted? Okay. Think. Isa lang naman sa dalawa, no? Okay. The no load condition is this should be shorted. Okay. So this is your no load condition. We short the output. We apply a test voltage at the input. You apply a test voltage at the input, you short the output. And that is how you determine G sub M. No? You determine this I sub O, you divide it by V sub I, and that is your transconductance. Okay. Note that if I left this open, ano magiging value ng I sub O ko? What if I had left that open? What would be the value of I sub O? 0. And therefore, your transconductance will end up being equal to 0, which doesn't make any sense. Okay. Now, what about voltage gain? So we have a circuit. We want to determine the voltage gain. Your voltage gain is your output voltage divided by your input voltage at no load condition. So for voltage gain, what is your no load condition? That should be an open circuit. No? Because if I short the output, ano yung magiging V sub O ko? 0, which doesn't make any sense. Right? So this should be an open circuit at no load condition. So if we're computing for transconductance, ang no load natin would be shorted. If you're computing for voltage gain, ang no load natin should be open. So where do we apply our test voltage? We apply our test voltage at the input. And then it becomes just a matter of computing for V out over V in. Okay. So these are all things that we already did last time, no? Review lang to. Okay, output resistance. How did we define output resistance? We said output resistance is output voltage divided by output current, output voltage divided by output current at zero input condition. Your zero input condition depends on whether your input is from a voltage source or from a current source. So yun yung in-explain ko just a while ago. No? Kung voltage source siya, short. Kung current source siya, open. Okay, let's just assume that it's from a voltage source. Okay, so we short the input. If we assume that the input is from a voltage source, ang test voltage ngayon natin, we apply at our output. No? And whatever the ratio of test voltage to the current drawn, that is your output resistance. And finally, your input resistance is your input voltage divided by input current, okay, at no load condition. Okay, at no load condition. So depending on the model that we use, depending on the model that we desire here. If the model that we're using here is the Norton model, ito ang no load natin. Okay? If the model we're using here is the Thevenin model, then our no load should be open. So it depends on the model that you want to apply for the particular two-port network. No? So here, I just assumed we're using the Norton model. So input voltage divided by input current at no load. That is your input resistance. Dapat madaling tandaan ito, no? It should be easy to remember. Output resistance, output voltage over output current. Input resistance, input voltage over input current. No? This one, zero input. This one, no load. Tapos voltage gain is easy to know. Voltage gain is easy to remember. What is voltage gain? Output voltage over input voltage. And then it is a conductance, so it converts a voltage to a current, so that's output current divided by input voltage. Okay? So those should be easy to remember. So all you have to remember now are under what condition those are computed for. Okay, and from that, you can either use this model or use this model. No? So meron tayong Thevenin equivalent, meron tayong Norton equivalent. And we already showed that if you just know 3, then you can get the 4th because of this formula. In other words, if I already know my GM and I already know my RO, actually I just need to know GM and RO, I can get A sub V. If I know A sub V and RO, I can get G sub M. We derived this formula last time. AV is equal to minus GM times RO. Again, take note, all of these are uppercase letters. Okay, low frequency analysis of transistor amplifier circuits. So this is what we're going to do now. Ito yung what's next, no? In my last slide before, what's next? We are going to use the unilateral hybrid pi model right now to analyze transistor amplifier circuits. So yun yung gagamitin natin sa EEE 123. Now this, I already mentioned this last time, this has its limitations because not all circuits are unilateral. But for the purpose of EEE 123, it's a good introduction and it gives a good indication of what the outputs are going to be. So what procedure are we going to follow? First, we're going to determine the small signal parameters of the transistor at the transistor's Q point. And to do this, we have to use large signal analysis. So, sanay na kayo dyan, ano? You've been doing that since 123, since EEE 123. No? Given DC excitation, compute for DC currents. So that's really just determining the Q point of the transistor. Okay. So once you determine the Q point, you can get now the small signal parameters. Okay. What are the small signal parameters? Okay, for a BJT, what are your small signal parameters? You have GM, okay, you have R pi, and you have RO. No? And for your MOS, let's say for an NMOS, no? Okay, you also have GM, okay, R pi is equal to infinity, open circuit, and then you also have RO. Do you remember ano yung GM sa BJT? You remember? Yeah, this is ICQ over V sub t. Okay. Then R pi is equal to beta over GM. Okay. And then what's RO? RO is VA, early voltage, divided by ICQ. Okay. Dito naman, GM, this is 2 IDQ over VGSQ minus VTH. Okay, R pi is equal to infinity. What is RO? This is lambda IDQ over 1 plus lambda VDSQ. No? So these are your formulas. No? So you just have to remember these formulas. No? So to be able to compute for GM, R pi, RO, you just need to know your quiescent point. No? Here you need to know your quiescent collector current. No? Here you also need to know that. Of course, your early voltage is a constant. No? Dito you need to know quiescent drain current. You need to know VGSQ. Okay, to be able to compute. No? Okay, let me get rid of that. No? That's step 1. Okay, step 2, you add the signal equivalent of the components that are external to the transistor. So dito sa step 1, ang dino-drawing lang natin is yung small signal equivalent nung transistor. Sa step 2, idadagdag natin yung small signal equivalent ng ibang mga components natin. So these are our capacitors, inductors, resistors, and our supply voltages. Okay. Note that sa module 5, in module 5, we're only doing low frequency analysis. No? Yung high frequency analysis, gagawin natin yan sa module 6. Now, when we're talking about low frequency analysis, the assumption there is that your capacitors are equivalent to what? What are your capacitors equivalent to? Nakasulat dyan eh, no? Basahin nyo na lang, no? Equivalent to short circuits, right? At low frequencies, X of C is equal to 1 over omega C. If omega is equal to or close to 0, X of C becomes, no, that's not the point, no? At low frequencies, capacitors can be considered short circuits when F is this is wrong, no? This is not at low frequencies, at the frequency of the input signal, no? At the frequency of the input signal. I better correct this. Okay. No, sorry about that. I just did this just now. No? So at the input signal frequencies, the capacitors can be considered short circuits. Okay, this is dito sa module 5, no? Sa module 5. And then we determine we determine now the unilateral hybrid pi parameters of the entire circuit. No? Dinagdag na natin yung external components, then we now determine the unilateral hybrid pi parameters of the entire circuit. No? And then we compute for whatever we're interested in computing for, using now the hybrid pi model of the entire circuit. So those are our steps. Okay. Now, what are the small signal models of our external components? Okay. For external components, sorry about that. So for external components, okay, the small signal model describes the change in voltage for small changes in current. No? Kaya small signal, no? The change in voltage, small changes in current. No? In other words, we are getting, okay, dV versus dI. No? The change in voltage for small changes in current. No? If I have a resistor, okay, what is the relationship between I and V? Baliktarin natin, no? Let's put V here and I here. Okay, let's put V here and I here. Okay, V is equal to IR, no? That's Ohm's law. So you just have a straight line, no? Where the slope of that line is equal to R. Right? So what is DVD? What is dVdI? That is just equal to R. Meaning to say the small signal equivalent of a resistor will also be a resistor. Okay, if I have a voltage source, by the way, no, that is going to be true also for capacitors and inductors. The small signal equivalent will also be the capacitance and the inductance. For capacitors and inductors, I don't want to get into that now, but you have to think of it in the S domain. The small signal response of a capacitor or an inductor in the S domain is the change in voltage in the S domain divided by a small signal change in current in the S domain. No? So for a capacitor, that would be 1 over SC, and for an inductor, that would be SL. No, I think you already studied that in 133, ba? Okay, so the small signal model for your capacitor and inductor will be similar. No, and then if you have a voltage source, so what does your voltage source look like? No, if I plot V versus I. No, by the way, this should be small. No, V versus I. No, V versus I. If you have a voltage source, what would that look like? No, that would look like this. Right? This is an ideal voltage source, where this is capital V. So what is dVdI? 0. So a voltage source is a short. The small signal equivalent of a voltage source is a short. And if you have a current source, So if this is my voltage, this is my current. Ang current source ko naman ganito. What is DVDI? What is DVDI? Wake up. Infinity. So my current source is an open circuit. Actually, this is the mathematical way of modeling external components, ano? But you can also think of it in terms of superposition. I mentioned that earlier, no? Remember, we're splitting up the analysis of a signal with we're separating the DC analysis from the AC analysis, no? And when we're doing DC analysis, okay, so you suppress your AC source, okay, then you do your bias computations, and then when you're doing AC analysis, you suppress your DC source. What do? You short your voltage source and you open your current source. No? So you can think of it the same way, no? Pag AC analysis or small signal analysis, you short your voltage source, you open your current source, and then you're only computing for the small signal response of your circuit. Okay, so let's take a very simple example, a fixed bias common emitter amplifier. So what does your fixed bias common emitter amplifier look like? I hope you recall. So usually you have your input. This is V capital I. No? You have a fixed bias. So your fixed bias, you have a bias resistor RB. And then this is connected to VCC. And then you have your load resistor or collector resistor, let's call this RC. This is also connected to VCC. And you get your output at your collector, that is V capital O. So let's assume you already computed for the quiescent currents and quiescent voltages. No? So nakuha na nyo yung quiescent currents and quiescent voltages. Okay? And therefore, you already know the small signal model of the transistor. No? So this is your collector, this is your base, and this is your emitter. Okay. So let's draw the small signal model. The small signal model. So we'll start with the base. Okay, what do you have from the base to the emitter? You have R pi. You have R pi. Cute na nyo, no? And then your hello. Hello. Can you hear me okay? Jomar, mahina yata. Hello, hello. Mic test. Okay, thank you. Okay, so from base to emitter, you have R pi. So this is our emitter. From collector to emitter, okay, this is GM VBE, where VBE is this voltage, you know, your base to emitter voltage. Take note, no? We use lowercase for only taking into consideration the AC component. And then between your collector, so this is your collector, no? And your emitter, what do we have? We have R sub O. So that is the small signal model of our transistor. And then we have to add our external components. Let's add our external components. Okay. First of all, okay, sabi natin, you replace your supply voltages with its signal equivalent. The small signal equivalent of a voltage source is a short. Right? So our voltage, our supply voltage looks something like this, no? Yung VCC. That looks something like that, no? This is VCC. Right? So what do? You replace that with a short. So just to emphasize that, I'm replacing this now with a short circuit. So replace with a short. So ganun din dito. Okay. So what do we have? Yung RB is still RB, and RB is connected between your base and your ground. So this is, my emitter is connected to my ground. Between my base and my ground, I have RB. Okay. And RC, if you take a look at RC, that is connected between your collector and ground. So this is RC. Okay. And this is now my V sub O, okay, from collector to emitter, and this is my V sub I. Okay. That is my V sub I. So this is now the small signal model of the entire circuit. This is the small signal model of the transistor. I have incorporated now the small signal model of my other components. So now I can determine the hybrid pi parameters of my entire circuit. So let's start with GM. What is GM? Okay, you better start familiarizing, no? GM is output current divided by input voltage at no load. Okay, at no load. How do I apply no load here? What do I do at the output? No load. Open or short? Short, right? Because this is the Norton model, no? So we apply a short circuit. So pag no load, isu-short ko to, no? Okay. So now I get an expression for I sub O. To get an expression for I sub O, I just use nodal analysis dito sa node na to. You apply nodal analysis here. Okay. So what is my nodal analysis? I sub O is equal to, okay, V sub O over RC. Okay. The voltage across RC is V sub O. So that should give me this current, no? The voltage across RO is also V sub O. Okay. Take a look. V sub O is also the voltage across RO, so that should give me this current, no? So this is plus V sub O over R sub O. And then what is this current? That is plus GM VBE. But take note that VBE, the voltage from base to emitter, is also equal to V sub I. Okay? Note that VBE is equal to V sub I. So this is plus GM V sub I. Now, what happens when we short this? Ano nagiging value ng V sub O? 0. Kasi shorted siya. So actually, this is 0. This is 0, no? That is at no load. at no load. No load, no? No load. So I sub O is just G sub M, V sub I. So ano ngayon yung I sub O over V sub I? It is just small G sub M, no? Which is what we're trying to compute for here. So capital G sub M is equal to small G sub M. So yun lang yun. No? Capital G sub M is just equal to small G sub M. Okay, what next will I compute for? Let me compute for R sub O. R sub O. Ano yung R sub O? I'm just trying to make you remember. Ano yung R sub O? No? Output voltage over output current at zero input. Okay. Let's assume that my input is a voltage source. So what is zero input? Zero input is I short my input, no? So zero input, if I draw it here, I'll draw it very quickly. So I have RB, I have R pi, R pi, okay. This is GM V sub I, no? Because VBE is equal to V sub I, no? This is RO, and then here I have RC, no? RC. So R sub O is V sub O over I sub O at zero input. Now V sub O is a test voltage. So magkakabit tayo dito ng test voltage V sub O. We connect the test voltage V sub O, no? Okay, zero input, assuming the input is a voltage source, what do? We short the input. Okay, what I have to do is I have to compute for I sub O, right? Because I want to get the ratio of V sub O over I sub O. So, ganun uli, ano? Apply lang ako ng nodal analysis dyan to compute for I sub O, no? So what is I sub O? I sub O is V sub O over RC plus V sub O over RO plus GM V sub I. Okay. Do you notice anything here? What can I cancel here? Ano yung matatanggal ko dyan? Yeah, V sub I. Why? Kasi short natin yung input, no? So we can take out V sub I. No? This is because this is zero input. Okay, so what is I sub O? I sub O is just V sub O 1 over RC plus 1 over R sub O. No? So V sub O over I sub O, this is at zero input, which is equal to capital R sub O, is just 1 over RC plus 1 over RO, no? Which is actually RC in parallel with RO. Okay. Now, would it have made a difference? Would it have made a difference if my input were assumed to be a current source? I just want you to think about that. What if my input were assumed to be a current source? Would it have made a difference? It won't, no? Because if my input were a current source, ibig sabihin, I'll leave this open. No? But if I leave this open, there is no current that will flow through either of these resistors. So if there's no current flowing, my V sub I will still be equal to 0. And therefore, this will still cancel. Okay, this will still cancel. Now that's because this particular circuit is really unilateral. This is really unilateral. Later on, I'm going to give you an example showing something that's not unilateral. No? But this particular circuit is unilateral. My output does not affect my input. And that's why, regardless of whether we consider zero input to be a voltage source or the current source, lalabas yung sagot natin pareho. Okay. Ano yung natitira? R's of I. No? What is R's of I? R's of I is equal to V sub I over I sub I at no load. No load is a special condition. Okay. So, nakakatamad mag-drawing, ano? No load, no? So, assuming this is the Norton model, what is our no load? Our no load is the output is shorted, right? And then where do we apply our test voltage? We apply it at the input. This is our equivalent circuit going to be, sorry. Our equivalent circuit, we have a test voltage. This is V sub I applied at the input. Then we have R sub B nga ba? Yeah. R sub B. Then you have R pi. Okay. RO. RC. And then this is RC, RO. This is GM, V sub I. We short the output. But note, ano? If you take a look at this circuit, walang kinalaman to dito sa input. Right? Because this is I sub I. Okay, I sub I is just V sub I over RB plus V sub I over R pi. No? Which is V sub I 1 over RB plus 1 over R pi. No? So V sub I over I sub I, this is at no load, is just 1 over RPB plus 1 over R pi raised to the minus 1, which is RB in parallel with R pi. Okay. So now I have my complete model, right? What is my complete model? So this is now V sub I. Ang Ri natin, so this is R sub I, no? This is R sub I. Is RB in parallel with R pi. Capital G sub M is equal to small g sub M. So this is going to be small g sub M, V sub I. And then my R sub O, R sub O ko, is RC in parallel with R sub O. And then this is now V sub O. So ngayon, kung alam nyo to, okay, I can give you a problem, for example, saying, o sige, kung mag-apply ako ng V sub I dito na, let's say, 1 millivolt peak to peak, dapat masosolve nyo yung V sub O at that input. So you should be able to solve that now. If I give you an input voltage, you should be able to solve the output voltage and the. If I connect a load here, okay, you should still be able to solve for the output voltage. Kasi posibleng may load dito, no? posible, there will be a load here. No, that's possible. Okay? But, okay, huwag na muna nating guluhin. Ano? Are there any questions? Any questions? Sorry. VDE is equal to V supply. Any questions? Okay. Let's take another example. This time I'm going to see whether you can do it on your own. No? But I'm going to complicate things a bit. So my example is going to be a common source amplifier, but now it is drain to gate biased. It is biased from drain to gate. So naalala nyo, one of the biasing schemes of your MOSFET is you connect a resistor between your drain and your gate. No? So how does that look like? So this is a VDD. Let's just call this R sub D. So this is your MOS transistor. Common source, this is your output, V capital O. Okay. Your input is capacitively coupled, so this is V capital I. But then you have to bias your gate, no? For a common source amplifier, we know that yung input signal natin we have to pull up. No? We have to provide a DC offset voltage. So one way of doing that is by connecting a resistor between your drain and your gate. No? So let's just call this R sub G. So what is my small signal model? Again, no, at the frequency of the input signal, we assume that your capacitor is going to be a short circuit. No? And then your supply voltage is going to be also a short circuit. Your supply voltage will short this point to my ground. No? So what will my small signal model of the MOSFET look like? No? So we'll start with the gate. Okay. We know that between your gate and your source, so this is your source, that is an open circuit. That is for DC. Okay. And then between your drain and your source, okay, this is GM, V small g small s, where this is V small g small s. And then I have R sub O. R sub O is equal to lambda IDQ over 1 plus lambda VDSQ. Okay. So this is connected to ground. Okay. Where's my input? Okay. This is my input. That's my input, no? Because this is considered a short circuit. So my input is applied directly to my gate, dito, reference to ground. Okay. And my output is just, this is your drain. Here, no? V sub O. No? Let's add the external components. No? So ito, yung R sub D natin is connecting your drain to VDD, but VDD is connected to, the VDD terminal is connected to ground, no? So andito yung R sub D. What about this? Where is this? This connects, itong R sub G, connects your gate to your drain. So andito yung R sub G. So first, no, GM. Ano uli yung GM? This is IO over VI. Okay. This is at no load. That is at no load. So we apply the test voltage here. Basically, we apply a test voltage here. And ang no load condition natin would be short. And this is now I sub O. So why don't you try this? Gawin niyo yung sit work. Sabihin niyo sa akin ano yung value ng G sub M. Okay, I'll give you what, 5 minutes. If somebody has an answer, just please raise your hand. No, I'll go to you, or you can come to me, and I can tell you whether your answer is correct or not. So again, we're looking for the value of capital G's of M. Notice that this is not a triple E131 problem. No? What is this? This is a triple E123 problem, right? I can. We could have given you this problem in 123, no? Solve for I sub O in terms of V sub I, basically. That's what we're trying to do here, no? Solve sub O in terms of V sub I, so that you can get the ratio between I sub O and V sub I. Okay, I already have several correct answers, no? And so far, all of them are correct, no? Save for carelessness, ano? So yeah, let's just go through the solution, no? Okay, so what do we do? All we have to do is we apply nodal analysis to this node, no? So applying nodal analysis to that node, what is I sub O? I sub O is, kalimutan muna natin na zero yung V sub O, no? Let's just apply nodal analysis. So that's V sub O over R of D, okay, plus V sub O over R sub O, okay, plus GM VGS, no? Plus, okay, what is this current? Because you have four currents, no? You have one current here, another current here, and another current here. So what is this current? This current is V sub O minus V sub I over RG. So V sub O minus V sub I over RG. Itong VGS is also actually V sub I. Right? If you take a look, VGS is also V sub I. Okay. So since we said zero load or no load, this is shorted. So this is zero, and this is also zero. So ano matitira, no? I'm just going to get V sub I GM minus 1 over RG. Right? Therefore, I sub O over V sub I, which is capital GM, is just GM minus 1 over RG. Okay? Okay. Lubos-lubusin na natin, no? Compute for R sub I and R sub O. So just compute for R sub I and R sub O. Anyone? Rs of O? Kahit na Rs of O lang muna, no? Or Rs of I. Yeah, okay. Teka, sorry. Can I say again? Parang baliktad yata eh. Dali. Uh, parang to the -1 yan. Yeah, that's right, no? That's right. Yeah. Ito, yeah, that's right. No? Um, ano ito? This is for V sub I? Sige, I think medyo you got the hang of it, no? Good, no? Sige. Let's just do it together. What I will do is let me duplicate ko na lang to, no? Okay, so let's do it together, no? Let's compute for Rs of O. Okay, what did we say was Rs of O? Rs of O is V sub O over I sub O at zero input, no? In this case, we assume that our input is a voltage source, no? We're supplying a voltage source. So ano yung zero input? Zero input, this is just shorted. Okay? Kung shorted ang input natin, shortcut ko na lang, ano? VGS is equal to V sub I. No? If VGS is equal to V sub I, ibig sabihin, zero ito. No? Because V sub I is equal to 0. Right? So this is going to, sorry, hindi ko pala mabura. This is going to cancel. No? That's going to be equal to 0 or open circuit. No? And if you take a look, what you now have are just 3 resistors in parallel. No? Of course, you will come to the same result if you use nodal analysis. No? But what you're going to see is no, Rs of D, Rs of O, and Rs of G are all in parallel. No? Therefore, Rs of O is just 1 over Rd plus 1 over Ro plus 1 over Rg, okay, to the -1. No? And I saw no, most of you got that, which is good. Okay. Okay. What about What about Rs of I? So what about Rs of I? No? Rs of I is V's of I over I's of I at no load. So where do we apply our test voltage? Up here. This is V's of I. No load, so we short this. Okay. What is this current? No? This current. This is ISO of I. No? That current is this node voltage minus this node voltage divided by this resistor. But what is this node voltage? That is 0 because this is shorted. Okay. In other words, by the way, no, hindi na 0 to, no? This is no longer equal to 0. Meron ng value to, no? But the point is this is a short circuit. Baka malito kayo, no? Okay. So anyway, this is V's of I. This is 0. Okay. So I's of I is equal to V's of I minus 0 over RG. And therefore, V's of I over I's of I is just equal to RG. So, major trivial. Okay, I want to mention something which is important to take note of. Balik tayo dito sa Rs of O. Note that if my input had been a current source, I would have had a different result. Okay. If my input was a current source, I would have had a different result. Because ano yung zero input pag current source? Ibig sabihin open circuit yan. If this is an open circuit, this is no longer equal to 0. There will be some value here. Right? So sige, let's try doing it, ano? We'll redraw it again. So this is V's of I, R's of G, this is GM, V's of I. Simplify ko na lang, no? This is R's of O, and then this is R's of D. And then this is V's of O. Pareho lang yan, no? That's the same. Okay. So if the input, if a current source were connected to the input, then zero input would mean I equal to 0. That is zero input, or this is an open circuit. And R's of O will be your test voltage. No? You have a test voltage here divided by I's of O. No? So V's of O over I's of O at 0 input. Okay? Okay, pero yun nga, no? Current source, open circuit to. Okay. Kung open circuit ito, then that means that there is no voltage drop across your gate resistor. There's no voltage drop here. And therefore, the voltage at this node is also equal to V's of I. You follow? Kasi zero yung current, so wala kang voltage up dito. Therefore, the voltage here will also be equal to V sub I, no? And if I apply KCL here, let me apply nodal analysis here. What am I going to get? I'm going to get I sub O is equal to V sub O over RD plus V sub O over R sub O, okay? Plus, okay, yeah, this is GM V sub I. Okay, let me say something about, it's a shortcut ko ng konti, ano? Let me say something about this, no? Okay. If I have a controlled current source, okay, this is a voltage controlled current source whose voltage is the voltage across it, right? This is equivalent to a resistor whose value is 1 over K. That is equivalent to a resistor whose value is 1 over K. No? Bakit, no? Take note, ano? Ano yung current na dumadaan dito? The current that passes here is K times Vx. Okay? If I had a voltage Vx here, what would be my current? My current would be KVx. No? Vx over 1 over K. My current here would be KVx. So note that the two are the same. Two are the same. So actually ito, if this is VI and this is GMVI, then this is equivalent to a resistance equal to 1 over GM. Okay? So ang mangyayari, this is going to be, this is going to be VO 1 over RD plus 1 over RO, okay, plus GM. And RO is going to have a different value. It's going to be 1 over RD plus 1 over RO plus GM raised to the minus 1. Okay, by the way, no? If you did not do this, okay, if you did not do that, then there are other ways, no? Because what you have to do is you have to express this. Actually, it's obvious, no? Note that if this is zero, okay, then there's no voltage up here. Therefore, this is VI. And note that VI is equal to V sub O. Right? Nakikita nyo yan? So actually, itong VI, V sub O. No? So I just put this aside, no? Because it's something helpful for you to know. No? That if you have a controlled current source, if you have a voltage controlled current source that is being controlled by the voltage across it, it's just equivalent to a resistor. Okay. But anyway, it's obvious, no? It's obvious that this VO is equal to V sub I here because there's no voltage drop here. So lumalabas ganun din, ano? You're going to get exactly the same thing. Okay, so there's a difference. Bakit nag-iiba yung RO kapag current source or kapag voltage source yung input? Okay. Actually, that is the weakness of the unilateral model. Okay? That is the weakness of the unilateral model. Because if you take a look at, where's our model, no? If you take a look at this circuit, no? So forget the test voltage, no, and the short circuit output. If you take a look at this circuit, there is feedback between the output and the input. And that feedback is provided by this particular resistor. When there is feedback between the output and the input, then the output will already affect the input. And therefore, theoretically, hindi na talaga pwedeng gamitin yung unilateral model. Kasi yung output meron ng effect sa input. No? So whatever we come out with here, there will be some errors. But for the purposes of EEE 123, those errors will still be tolerable. Okay, so ang mangyayari na lang nito, if you encounter a problem where you have to impose zero input, then you have to know the nature of your input signal, whether it's a current source or a voltage source, so that you can apply either a short circuit or an open circuit accordingly. Ganun na lang, no? Okay. But I just wanted to explain to you this because you also have to understand na yung unilateral model has its limitations. Okay? Are we clear on that? Okay, I don't have time to, I intended to do this common emitter, common source amplifiers with the generation resistor. But I'll ask you to do this, ano? Kasi you already have a good idea in mind of the process. Okay, what is an example of a common emitter amplifier, for example, with the generation resistor? So we took this up. This is an example. This is your degeneration resistor RE. So let's call this RC, let's call this RB. Let's say this is VCC. This is V capital I, and this is V capital O. Okay. This is your generation resistor. What will our small signal equivalent look like? Okay, so this is my base, this is my collector, this is my emitter, I have R pi. Okay. Collector to emitter, I have GM, V, small b, small e, where this is small b, small b, small e. And then I have R sub O. Okay. Now this is where it gets a little bit exciting. Between E and ground, I have RE. Okay. Between my base and ground, I have RB. Remember, VCC is equivalent to a short circuit to ground. No? And then between my collector and ground, I have RC. So this is now V in. Let's just indicate it as a node voltage, and this is VO. That's VI and VO. So, example, ano yung GM? GM is I sub O over V sub I at no load. At no load. So anong gagawin natin to compute for G sub M? Exactly the same thing. No load, so i-short natin to. And then magkakabit tayo dito ng test voltage. So this is V sub I. That is our test voltage. And then we compute for I sub O. Right? So you compute for I sub O divided by V sub I, and that is going to be GM. So yun ang subukan yung gawin on your own. Okay. Try doing that on your own. So this is just an exercise for you to do. Again, you take a look at this problem. It's really more of a triple E 1, 2, 3 problem. No? What you do is you get an expression for I sub O, and you try to eliminate in your expression for I sub O, you try to eliminate all the variables except V sub I. No? Because if you can express I sub O in terms of V sub I, because this is a linear circuit, it's a linear circuit, you will be able to get the ratio of I sub O to V sub I. Dahil linear siya. No? You won't be able to do that if this is nonlinear, but you can do it because this is linear. And whatever that ratio is, that is your G sub M, because these are your no-load conditions. So subukan yung gawin, and then we'll continue discussing next meeting. Are there any questions? Okay, if there are no questions, then that's all for this afternoon. Okay. Thank you.